Section 5.4 Interactive Assignment Objective 2. Suppose that a computer chip company has just shipped 5,000 computer chips to a computer company. Unfortunately, 50 of the chips are defective. We want to compute the probability that two randomly selected chips are defective using conditional probability. In Part B, the probability that the first randomly selected chip is defective is 50 out of 5,000, which is equal to 0.01, which is equal to 1%. We want to compute the probability that two randomly selected chips are defective under the assumption of independent events. Okay, so again, we have 500 computer chips here, and we know that 5 of the chips are defective. So we're going to use the conditional probability for the first part. Okay, now remember that to find a conditional probability, the following rule can be used. The probability of event F occurring, provided E has already occurred, is equal to the probability of event E and F divided by the probability of event E, which is equal to the number of outcomes or times that E and F occur divided by the total number of outcomes of event E. So we want to use the counting principle to find the counts. So we need to begin with the number of ways two defective chips can be chosen. So we know that 50 of the chips are defective, and we want to find out the number of ways that two defective chips can be chosen. So we know that there's 50, right? So if there are 50 defective chips, then there are 50 ways the first defective chip can be chosen. When a second chip is chosen, there are only 49 defective chips remaining. So we removed one. Therefore, there are 49 ways the second defective chip can be chosen. So there's 50 ways in the first, 49 in the second. So using the counting principle, to find the total number of ways to choose two defective chips is to find the product of those two counts. So we're going to take 50 and multiply by 49 to get 2,450. Okay, now we need to find how many ways there are to choose two chips. So how many chips do we have? Well, we know that there's 5,000 computer chips. So, since there are 5,000 chips, there are how many ways? There are 5,000 ways the first defective chip can be chosen. Now, when we remove that first chip, the second chip is being chosen. Now we have 4,990 chips remaining. So therefore, there are 4,999 ways the second chip can be chosen. So again, using the counting principle to find the total number of ways to choose two defective chips is to find the product of these two accounts. So we're going to take 5,000 times 4,099 to get 24,995,000. Okay, now we're going to use these two results. So we're going to divide to find the probability of selecting two defective chips at random. Now remember the formula. The probability of event F occurring, provided that E has occurred, is the following. The number of outcomes that E and F are, we would say that represents 2,450, because that's how many ways two defective chips can be chosen, divided by the total number of ways that two defective chips can be chosen. So again, looking at this, we can see what this says in words. The numerator is the probability of the total numbers of ways to choose two defective chips, divided by the probability of the total number of ways to choose two defective chips. So we're going to take those two amounts, 2,450 divided by 24,995,000. So let's see what happens when we do that on our calculator. So if we take 2,450 and then divide it by 24,995,000, then we get this following number here. Now what does that mean? Okay, well this is the number that we get. Okay, what this means is a scientific notation number. And what this tells us is the following. This says that this is 9, let me go ahead and change that there. This is 9.8019,604, and that E is telling us that we're timesing this 10 to the negative 5th power, which means we need to move this to the left 5 times. So if we move the decimal place to the left 5 times, 1, 2, 3, 4, 5, there is our decimal. So we have 1, 2, 3, 4 zeros here. So we end up getting 0.000098,019, and they want us to round this to the nearest 8 decimal places. So this 9 is telling us to round up that 1 to a 2, and therefore there is our result. We would say that the probability is 0.00009802. And let's take a look at our result, and there is our answer. Okay, now for part B, the question is the following. It says the probability that the first randomly selected chip is defective is 50 out of 5,000, which is equal to 0.01, which is equal to 1%. Okay, and so what it's saying here is that we want to compute the probability that 2 randomly selected chips are defective under the assumption of independent events. Now remember that when E and F are 2 independent events, then the probability of E and F is equal to the probability of E times the probability of F. We're going to use this multiplication rule with the given probability for finding 1 defective chip to find the probability of choosing 2 defective chips under the assumption of independent events. Well, again, the formula, the probability of E and F is equal to the probability of event E times the probability of event F. Now, if we take a look, we know that we're given the probability. Okay, so the probability of E is given, which is 0.01. And the probability of event F is also 0.01. So what we're going to do is we're going to take both of those and multiply them together to get 1.0 e to the negative 4. Now remember, this is the same thing as 1.0 times 10 to the negative 4, right? Okay, so what does that mean? Okay, that means that if we take 1.0, we're going to move this to the left 4 times. 1, 2, 3, and then 4. So we have 0.0001. So there's our 0.0001, and they're asking us to round this to 8 decimal places, so we add the 4 zeros. So we're going to say the probability is 0.0001000000. Okay, and if we take a look at that result, there is our answer, rounding it to 8 decimal places. Okay? Okay, now the last part of this question states the following. It says, when small samples are taken from large populations without replacement, the assumption of independence does not significantly affect the probability. Based on the results, what does this mean? Okay, what it means is, when it talks about this question, it says here, without replacement. The first example, okay, we took out a chip and didn't put it back in. That's why we're taking 50 times 49. Same thing over here. So this is without replacement. The second one, we used the same probability. So this was with replacement. So the question is saying when small samples are taken from large populations without replacement, meaning the first example, the assumption of independence does not significantly affect the probability. Based on the results, what does that mean? Well, let's take a look at the probabilities we got in the first answer. Notice that the two probabilities, 0.00009, if we round that to the fourth decimal place, it'd be 0.001, which is the same thing as this probability that we got in the second problem. And they're nearly the same. So when small samples are taken from large populations without replacement, the assumption of independence does not significantly affect the probability. So then we would select that following answer. We would say that the probabilities are nearly the same.